Okay, I'm gonna again let maybe like wait for until 3:05 for more people to join. Again, this session is being recorded again, and I will share the link to the recording at the end. Maybe like an hour. Usually takes at least half an hour to be ready, and then as soon as it's ready, I'll share that link for you to watch offline. I want to also mention that we have today we have two people that are also developers of PRISMS-PF, and they are in Professor Thornton's group, and they will also be able to help us with questions. I think what I'm going to do is I'm going to open a breakout room for questions. So, we can have some questions here in the main room. And if somebody has, if there are too many questions, there are more than, we can have two breakout rooms. That way, people can, there's a space for more questions. So I'm going to create a breakout room, and then people choose, let it just choose that room, and I will call it questions. Call it questions room. Okay. And then if you want to join the room, just you should be able to see it, and you can just join it if you have a question. And then I'm thinking either Vishwas or Yanjun can join the room, and
sure. So are we having breakout rooms?
Yeah, we're having breakout rooms, and then if there's many questions here, or there's more than two questions that you think you can answer, somebody can join the breakout room, and you can answer either yourself or Yanjun.
Sounds good.
Mm-hmm.
So just please let us know beforehand if people are going to breakout rooms.
Yeah, so
exactly. Send a message or something so that we know you are in the breakout room.
Exactly. And in general, you can just ask the question. You can either unmute your microphone, but in general, it's better if you just ask a question in the chat. You can just ask a question anytime. And I'm going to ask either Vishwas or Yanjun, if you know the answer, if you can answer that question, just answer it in the chat as well.
Sounds good.
Thank you. Okay, so almost there. I did send an email earlier today about downloading some of the materials for this training. I hope you're able to download them. If not, I'm actually going to do it right here. Hopefully, it'll just take a few seconds. It'll contain all the materials that we're going to be using today, including some output files from PRISMS. These output files, I'm just creating them because just to save time, I'm just having them uploaded so that we don't have to run simulations and just wait for the simulations to be done. Although they're not large files, and they wouldn't take like a lot of time to run, maybe a few minutes. But okay, so let's get started. So this is the training session 2. I'm David Montiel. As I mentioned before, I'm going to have Vishwas Goel and Yanjun Liu, who are also work a lot with phase field, and they are PRISMS developers as well. And I want to thank them for being here to help us answer questions. So let's just start. So today, what we're going to cover is actually, I want to just maybe answer some questions about the exercise that we left yesterday. or any of the exercise of the problem set that you may have tried, or just basically any questions about yesterday's session. It doesn't have to be 10 minutes, maybe it could be less. Then I will talk about some of the tools to visualize results and analyze results. I will have an overview of the post-processing scripts that are available in PRISMS-PF and what they do. And we'll have a couple of in-class exercise on questions. Okay. Hopefully we'll be done, early, and then people can just stay and, try some exercises. And then we can just ask questions. Or you can just, take these exercises and try them at home or whenever you want. Okay. So this is kind of the same what I showed yesterday. Just a reminder that we have this GitHub repository that includes all the training materials and also has this presentation. Sorry, the arrow is pointing at the wrong file. This presentation here is at PRISMS-PF training session 2. And you'll be able to download all the materials from there. And also as you can see, there's a new directory called training data. And all the files for analysis that we're going to use today are included in there. Okay, so let's start with some questions. Was anybody able to solve the problem yesterday, or do you have any questions related to the problem that consists on adding a term to the free energy to tilt the double well? So
it all worked. I can say all seems to work well.
Right, great. Yeah. So, I mean, if you can just maybe like, why don't, let me see if we can do a poll, or if you can just raise your hand if you were able to solve the problem, or those of you who were able to solve the problem, or at least got a solution. And I'll share the answer right now, but first I want to see how many of you actually did the problem. Okay, so I see Marcel tried it, he did it. I'm not seeing any other hands. That's fine, I guess. But you guys are busy with other training courses, so I can just tell you the answer is so we have again a double well term that that we are include in the bulk component of the free energy, and this will tilt the double well, making the beta phase thermodynamically more stable than the alpha phase. And if you put the parameters that we had in that problem that I have in the slides, you should get a final microstructure that looks like this for time 50. So as you can see, there's a lot more red area, a lot more of the beta phase than in the case without that original term, undercooling term. So kind of the results make sense. In that sense, if we actually let the simulation run, definitely you would just get all a single phase. So this is what you should get. So if you you want to keep trying that problem on your own, you should be able to compare with these results because you'll be able to access the slides. Okay. So let's keep going. And I just want to mention some motivation for today's session. And it's that data visualization and analysis are key components and necessary to make sense of the results in computational material science. And simulation outputs often consist of large data sets. And this requires tools that can efficiently use computer resources, including compute engines that can run parallel on a cluster. So actually, Visit has that capability, although we're not going to look into that today. But both Visits and PRISMS-PF are able, PRISMS-PF can output parallel results on separate files, and Visit is able to read these results and plot them on a cluster, which makes visualization a lot faster. And then two of the main or most popular tools for visualization and analysis are Visit and ParaView. They're both open source, and they have a lot of functionalities. I preferred Visit, kind of just because this is the first one that we started using here at PRISMS, at least for phase field. But ParaView, basically has all the same features, and it's just a matter of preference. To save time, I'm going to talk about Visit, and also because the post-processing scripts that are included in PRISMS-PF use Visit libraries. So if you go to the link, you can get the user's guide. And today we're going to cover, opening databases. We actually did that yesterday. So we don't really need to do that, although we have to do it today as well. Then I'll show you how to make some basic plots: the pseudo-color plot, contour, spreadsheet, and line-out plots. Some operators, which include slicing or selection. I will show how to do queries, which is basically results for data analysis. Things like integrating over a volume, finding the interface length of something, or finding the dimensions. There's many options, and I will go through some of them. And then also how to define expressions with the variables that we have, derived from the variables we have. I'll show you a little bit about how the commands window works, which is very useful to have to automate processes. And also, finally, I'll talk about how to create scripts using Visit, which is the basis of the post-processing scripts from PRISMS-PF. And then it allows us to automate certain tasks and speed up our work. All right, so I am going to soon start an interactive session, but first I want to mention that we are going to look into a database that has the results of a simulation of alloy solidification. So in this case, what we have is the dendritic solidification of an alloy under constant cooling rate. So imagine you're here in a phase diagram where we have temperature in the y-axis, and we have alloy concentration on the x-axis. And if we have a liquid and we start cooling down along the at a constant, we have an original constant composition, and then we start from liquid and slowly cool down to get the solidus line. What we are going to see is something. The solid, as you can see here, is the red region, and liquid is the blue region in the order parameter plot. And we will observe dendrites due to a morphological instability that results from inhomogeneities in the concentration that tend to amplify. And if you look at the concentration plot here, this is because this has a partition coefficient less than 1. That means that the solid would have a lower equilibrium concentration than the liquid. And as the domains solidify, there is solute rejected close to the interface, and that rejected solute slowly diffuses into the liquid. So what you're seeing here is the concentration gradients of the solute within the liquid. Okay. Oh yeah, okay, so now let's go to I'm going to close this, and I will just look into the virtual machine. So hopefully you'll have your virtual machine already open. If not, please open it. And if you're here, the first thing that I would like to do is open a terminal. And I am going to download the training materials for today. So I'm going to type git clone. I'm going to, basically this just downloads all the materials, all the repository, and it'll create a new directory. By the way, are you able to see the terminal? If you are not able to see it, please write it down in the chat. Thank you. And you can see what's been written, right? Okay, so let's so now that we have cloned, if we just look into the contents of, this is the home directory. If you just look into the contents of this home directory, there will be a new directory called PRISMS-PF training materials. So I'm gonna go and switch to that directory. Okay. And then I'm going to switch to the workshop 2022 branch. So the way that we do it is git checkout. Actually, let me just first do git branch, and that's going to show me the branch that I'm on, and then we're at the master branch. But if we do git checkout, and then workshop 2022, it's going to switch to that branch. And if I go back to say git branch, now it shows me that I'm in branch workshop 2022. And if I list the contents, you'll see that now I have the slides, the exercises, the cheat sheet, and the training data. And then if I list the contents of the training data, you'll see two directories, one called alloy solidification, another one called nucleation. And if I list the contents of alloy solidification, you'll see a bunch of solution files, which is what we're going to start first to look into some of the PRISMS features, right? So actually, let's go to this file, and then let's open and visit from within the terminal. Oh, sorry, copy paste is weird here. And I'm going to open visit. If you open it within the terminal where the files are, you won't have to navigate to open the database. You won't have to navigate to that directory. It'll already be in that directory, right? So let's open. And as you can see, I'm already in alloy solidification. So I'm going to select all the files. Okay. Sorry, did somebody have a question, or is it just a microphone? Okay. Okay. Right, so let me, I've already opened this. So I'm going to just show you some of the plots that we can do. I already show you the pseudocolor plot. So let me plot first using this to plot the order parameter. And I showed you also how to look at different times. So this is just showing, you know, the microstructure at different times, right? And then you can just move, or you can just use this buttons here, or you can just drag the slide, or you can just use this switch to create kind of an animation here. Let's add another plot. You can just add as many plots as you want. Let's add another plot for this, for the concentration variable. And if we draw it, it's just going to replace the existing plot for the order parameter. And as you can see, we sort of see the same shape, but now you see this kind of halo, you know, this reddish, yellowish halo, which represents the concentration gradient as the solute is segregated away from the interface, right? And then at late times, you know, we almost see a uniform concentration in the liquid. Okay. So that's the pseudocolor plot. You can do stuff like if you just want to have both of them, but you want to see, you know, go back to seeing you can hide the concentration plot and it'll just show me the order parameter plot. Or vice versa, I can hide some of the plots. Yeah, that's pretty much it. You can also define some of the properties of the plots. So if I go here, I can set the limits of the maximum and minimum values that I want to be represented. I can choose the color table that I want to use to plot. You know, I can choose, for example, you know, there's, you know, say spectral. And then if I apply, it's just going to show me different colors, right? And well, there's many features that we can do, but you know, this is kind of just something that you can just explore and see whatever you like. These are these settings, right? Visit for some reason has this thing where it overlaps part of the plot with the labels. So what I like to do sometimes is if you go to controls and view, I can change the viewport, and if I just put 0.95, this is kind of like the y coordinate of the viewport, the top y coordinate, and apply. It's just going to make some space for the label here. Okay, let me show you now an example of a contour plot. So I'm going to add another one, and this is going to be contour. So I'll go here and I'll choose a contour of the concentration. And let's see how this one looks. Let me hide these two. I'm going to hide this one, and plot this one. So that's, you know, this gives us the contour lines that represent constant values of the concentration, right? So it means this tells us like the solid has an approximately constant concentration. It's basically just choosing 10 lines over the whole range of concentration values. And it chooses 10 equally spaced values, and then it plots lines along those values. Okay. So usually, though, it's more helpful to say, for example, if I want to see what the interface is, I can go to the settings for the contour. And instead of saying plot me 10 levels, I'm going to say plot me 1 level, but choose that by value, right? For example, here, actually, this is a little tricky, but not actually, let me not do this in the concentration plot, but let me do this in in the order parameter plot. So I'm going to add another plot, which will be a contour, but of the order parameter. Okay. And then for the settings, I'm just going to say, don't choose 10 labels, choose a value where the order parameter, remember, if you remember, the order parameter usually goes from 0 to 1. In this particular application, it goes from -1. So the liquid is represented by -1 and the solid is represented by +1. And the interface, the middle of the interface is like the value of 0, approximately, right? So if I just say select by value of 0, it's going to just give me the middle of the interface. So let me draw this. And let me hide the other one. Okay, so this red line tells me precisely where the interface is. Right, and if I don't like red, for example, I can go here and I can change the color and say like I like black. Oops, I don't know what's happening, sorry. There you go. See, now it's in black. Okay, so these are some of the plots that we have. Another plot I want to talk about is, for instance, if I just want to see the values, I can do like a spreadsheet. For example, let me do a spreadsheet of the concentration. And if I draw it, this is going to show me the values of all the nodes. This is actually more helpful. This is just kind of, it's just plotting the values of all the values that are there, but in no particular order, because we don't have an unstructured mesh, which means that let me actually show you the mesh first. That would be probably a better thing to look at. So let me hide these two and show you a mesh plot. I'm going to show the concentration, or not the concentration. Let me show the order parameter. And then let me plot the mesh on top of that. Okay, so as you can see, this mesh is more refined in areas around the interface and a lot less refined in bulk regions, right? Let me do a zoom. Actually, if you select this magnifying glass and then you select a region, it's going to zoom into this region, right? So you can see it much better here. In order to solve for the phase field equations, you need to have a much higher refinement in the region of the interface and around it. So basically the spreadsheet plot, the reason it's not structured is because every node, it basically just numbers every node, and every node has a set of coordinates, but it doesn't, because it's not a regular mesh, a uniform regular mesh, it doesn't appear, the values do not appear order in a mesh. But if you actually, this is probably a good idea to go to, I'm going to talk about operators later, but let's say that we create an operator on this. Let me hide this for now. And then I'm going to create an operator on, operators are things that act on plots, right? So let me go back and recenter this plot. Okay. And then I'm going to apply an operator on the plot. So I select the plot, and the operator is that I'm going to apply here is called resample. And then this is going to create a uniform mesh of the resolution that I want. So I'm going to go here, double click here on operator properties. And what I'm going to do is I'm going to unselect 3D resampling. And I'm just going to say, just do 10 mesh, 10 in each directions. And since the system is kind of elongated, I don't remember the aspect ratio right now, but let's just say it's 1:5. Ideally, you want to choose, the number of samples so that it represents the aspect ratio of your system. but for now, let's just say 10 to 50. And then I'm going to apply and then dismiss. And I'm going to draw, right? So, oh, that doesn't look good. Let's increase this to maybe 50 and 250. And apply and then dismiss. So now it's resampled, as you can see. Kind of just lost a little bit of resolution, but you can make it as fine as you want, right? Obviously, you're not going to get more information than the highest resolution that we have for the simulation. If you resample to like a very, very high, use a lot of sampling points. But now what we have is a regular mesh. And if you look at, if we add the mesh plot to this, it should hopefully, let me see, no. Resampled mesh. Let me see. Yeah, so now it's resampled mesh. So let's see, yeah, so now it's uniform mesh, right? And now if I add an operator of this, basically, by the way, this operator acted on all of the plots, right? You can also ask the operator to not act on all of the plots. If you select this, you know, it's not going to be applied to all of the plots, but now it's being applied to all the plots. So if I add a new plot that is the spreadsheet, now it's going to have the mesh. It's going to be resampled as well, and hopefully now it'll show us like an Excel spreadsheet, right? So now you can just copy this data to, you know, or export it, and then open it at an Excel spreadsheet or a MATLAB, or in any file that you want, any CSV file or any file, and then you can just use open the data somewhere else and use it. Okay, so these are just some examples of the plots that you can do. There is one. Let me just delete all plots for now. And I'm going to back to adding a pseudocolor plot of the concentration. Now this one isn't resampled. And then let me add, the last plot that I want to show is a type of plot that's a line out plot. So if I select this one here, this kind of, you know, X versus Y plot, and then I just put my cursor on the image and then, you know, put my mouse and then click and then leave the mouse on. As you can see, there's kind of like a line forming. So this line, when I release, will create a new window and it'll show me the values of the concentration along this line that had appeared. Oops, I don't know what happened. Sorry. Oh. I didn't want that to happen. There it is. Let me kill this plot again. Yeah. So anyway, I hope you got to see it. Let me plot it again. Hopefully this will. I won't move it this time. I just wanted to move it to show you the original. I'm going to show you and go back to the original window, and so it's going to plot me the values along this line of the concentration. So that's also helpful, right? If you want to know, okay, along this direction, how does the concentration look like, right? So that's the line out plot. And then of course you can adjust in the line out plot. You can adjust the limits. So so this is in Windows 2, right? So I'm going to go to window 2 by selecting active window 2. And as you can see, it's showing the line out plot. And in the properties, I'm going to double click here. And then it shows me which points are, so it's giving me X, Y, and Z coordinates, right? So for example, if I want to make sure that it's horizontal, point 1 and point 2 should have the same y coordinates, right? So by moving this, and then let's say I just copy this value. Let's just, sorry, let's just do 145 for both. Okay. 145. So 0 is just 0 in z direction, so it doesn't matter right now. So yes, you can see it kind of changed because now it's representing a region that is like a horizontal line, as you can see here. You know, it's not the greatest color, it's green, but you can still see how it represents that. Okay, so now these are kind of the main plots. There's obviously lots of other plots, but you know, I advise you to read some of that documentation and manual to look into the different types of plots that you can do. Now, talking about operators, I already
just to add one small thing, if you want,
Yes.
if you want to have it side by side, right? The two windows.
Yeah.
You can use this. Let
This?
me just rotate that real quick. Yeah, this. So if you do that,
Nice.
that's
Thank
it.
you.
It'll give you side by
Thank you,
side.
Vishwas. I never used that. Thank you very much. That's really helpful. Okay. So, all right, let's just delete this plot now for now. And I want to talk about operators now. Let's go back to the original view. So let me see, how am I doing with time? I think I'm doing well. So one of operators, different operators that you can use, for instance, is if you're wanting to create a slice of this. This actually works more for a three-dimensional plot, but you know, I can add a slice. Let's see what happens. And if I add a slice of this, let me see. So basically this is, again, because it's a one-dimensional plot, it's just adding a slice at x equals 0, right? So in 2 dimensions, you can have a 3-dimensional pseudocolor and then add a slice of that. Unfortunately, I don't have like 3D data right now, but it'll add a slice of the. Obviously, you can't see a three-dimensional data. You can see everything all at once because you would have to penetrate the volume. But if you add a slice or 3 slices, then it allows you to see a particular transverse cut of the system, right? So that's, you know, very useful operator. I also want to talk about an operator that allows us to, let me remove this operator first, back to what we had. Another operator that allows us, is very helpful, for instance, is a selection operator type. And what this will do is create basically crop the system according to some criterion. So you can say, I want to just have the system, you know, I want to crop the system to a box or a rectangle in 2D, different shapes. But one of the most convenient ones is the isovolume operator. So for instance, I can just say, all right, I'm going to create the isovolume, but I want to make sure to select all the liquid region and then not plot any of the solid region. So what I'm going to do is I'm going to say for the variable of the order parameter, so we're plotting the concentration, but we're going to plot it based on the value of the order parameter. And if you remember, solid is -1. Sorry, solid is +1 and liquid is -1. So everywhere between -1 and 0 will be liquid, right? So if we put a minimum of whatever the minimum value that exists in the system and the upper bound is 0, is going to select the liquid region. It should select the liquid region, but based on the value of the order parameter. And then hopefully this will work and show me only the liquid. And as you can see, you know, this white, it's kind of not part of the system, right? So this is very very useful. Another, for example, if I want to see what the concentration looks like around the interface, I can say, well, plot everything that goes from negative 9.99 to positive 0.99. It should just show me, you know, everything around the interface. We can even put another 9 in here, see what happens, right? So everything here is showing me the concentration all around the interface. Okay. Now, let me show you another operator that I find useful. And that is the operator, another slicing operator called isosurface. So isosurface operator is almost like a contour plot. First, let me go back to plotting this. So now I want to create, for example, if I wanted to show see where the interface was, I could just add a contour, right? If I just want to know where it is. But suppose I want a plot that shows the value of the concentration along the interface, right? So see, what I can simply do is, and I'll add an operator that will select, that will slice. You'll create a 2D surface, right? Or in this case, a 1D surface. And I'm going to set it to be a certain value. And I'm going to choose the value of 0, but I'm going to choose the value of 0 for the order parameter. So again, we're plotting the concentration, but we want to plot it at 0 order parameter, which is exactly in the middle of the interface, right? So if I apply and then draw, right, then this is what we're, so here the green is not just as a fixed color. If the interface had a different concept, if the concentration of the interface changes, which actually it does, then the color of this plot should change. Actually, this is a good opportunity to show you actually how to fix we can actually just fix the range of values. And let's just say I'm going to go from 0 concentration to 10, and then I'm going to make sure that it's fixed from 0 to 10. So then the color bar, the scale of the color bar won't change with time. So let me apply and then draw. And hopefully this, as you can see, yeah, the concentration is going to like light blue, like cyan, and then it gradually becomes more green, which means it's increasing, right? The concentration at the interface. So that's just one example. Sorry, somebody drew something. I'm just gonna remove it here. I'm trying to move this here so that people can see. Okay. Now, that is the isosurface operator. And, I already showed isovolume. And now, actually, let me, this is a good opportunity to go to things like query. So, let me see. Actually, let me go to something else. Let me go to expressions first. So, all right, I'm going to delete this isosurface operator. So, okay, we're back here. Oh, it looks weird because it's not changing. Let me go back to not setting limits. All right. let me go to expressions. So if you go to here, controls, and then expressions, right? What if we want to do, we don't want the order parameter to go from -1 to 1, but we want to see a plot of something that is like the order parameter, but you go, it takes the usual values of the order parameter from 0 to 1. So we can do like a mapping of the order parameter, and then we can just call it phi mapped from 0 to 1. Let's say this is just the number of the variable that I can call it whatever I want. And then I'm just saying that the way to map this is to add the value of 1 to phi. This is in the definition, right? And then I'm just going to divide by 2. And then this is just from the order parameter goes from 0 to 1. Sorry, from -1 to 1 to the interval 0 to 1. And I'm going to apply, dismiss. Okay. And let me delete this and add another pseudocolor for this new map. So now this new variable appears in the list of variables that I have access to. So I can just plot this new variable that I define as a new expression. Okay. So as you can see, it looks exactly the same as the old order parameter, but if you can see the limits here, as seen in the color bar, we're having a value that is very, very small, 10 to -6, as a lower limit, and it's almost 0, and then 1 as the upper limit, right? So we've effectively changed the scale for the order parameter. Now let's actually go to another thing that is interesting, that is queries. So I'm going to go again back to controls, and I'm going to select the query menu. Okay. And again, as I mentioned, queries is just data analysis built-in functions in Visit. So for example, one of the ones that is most useful is this one called weighted variable sum, which is just really the integral, right, of the whole, the integral of the active plot. So the active plot is this phi mapped, and if you actually calculate the integral of the order parameter, it'll give you the volume of the area that is equal to 1. And I hope to convince you of this. If you can just imagine that you have an order parameter that is 0 in the liquid, right? And then 1 in the solid, right? And then, some in between value in the interface. And if you integrate, right, this would be just represent, sorry, this is 1. And then it's a 0. And then this is, I'm just representing this, let's say, in the x-axis, right? If you integrate over this direction, it's just going to give me the area, well, here in this case, the length, because it's a 1D example, but in 2 dimensions, it will be the area of solid, right? So let's actually calculate this. Let me go back to mouse. And let's do, if I just plot query, it's going to give me the area, right? So this is the area of the solid region, right? And if I have the volume of this volume would be the volume of the system, I believe. I think it's the total volume. Nope, sorry. Should have tested first. Anyway, there's probably an area, like a 2D area, and it's probably the area of the whole system. This makes sense. So if I divide this number by this number, right, it's going to give me the solid fraction, right, of the system, because it's the area of the solid phase relative to the area of the system, the total area of the system. And if I have a 3D thing, it's the same thing. If I get the integral, that integral divided by the total volume of the system, it's going to give me the solid fraction. And actually, this should be the same. This should give you the same. There's a property here called average. And you can actually show that the average is, in this particular case, for the order parameter, the average is going to give you the solid fraction, right? So here, you know, you have 0.2 something. So if you divide this number by this number, you should get this number here. So anyway, this is a lot of these are very useful. You can also do time queries, and then that will actually, you know, for instance, for the average value, and then I'll just actually give me this result, you know, over time. So, and it's going to plot it, right, in a new plot. And so this, for example, this is telling me how the solid fraction evolves over time of the system, right? It goes from almost 0 to around 0.75 in the last frame. All right. So let's talk about. So I talked about query. Let me think of what else I can look into. I guess for now we're all set. You can look into different types of things that can be done by this. And if you actually just look at, I'm going to talk about the post-processing scripts in Visit later, and then you can see how other functionalities are used to calculate different things. If you just look at those scripts, they're pretty self-explanatory. But that one of the very powerful tools in Visit is actually, let me close this window. Right. So one of the very powerful tools in Visit is this thing called the command window, right? So this command window, let me clear this. So what this command window does is that, for instance, if I press record here, right, it's going to open a what's called a CLI window, and this CLI window basically just is, you can type all of these operations, right? They can be mapped to commands that you can just use, right? So if you see what these commands do, so what I can do is I'm recording, right? So everything that I'm going to do right now is going to be, when I stop recording, it's going to show the corresponding script commands are going to show here. So let's say that now I'm going to apply, I mean, we've already done this, but I'm going to apply an operator of this, and I'm going to select an ISO volume, and I'm going to show the ISO volume. Now, before I used to pick the liquid region. Now I'm going to show the solid region. So this solid region will be everything that corresponds to 0.5 onwards, right? In this case, because remember, this is now the mapped order parameter, not the one that goes from -1 to 1, but the one that goes from 0 to 1. So the interface is at 0.5. So let's do this, apply, and let's plot this. And as you can see now, I've selected the solid region, right? And then the liquid is empty. And then let's just say, okay, I want to be able to do that every time. You know, I want to be able to just do it many times, right? So what I can do is I can just stop this, right? And now it basically has printed the set of things that it did, right? Oops, sorry. Sorry, I maximized this window for some reason. Let me. Okay. I wanted to minimize it. So now I can press, I can just be in this window. Suppose that I, again, close this. And now I can press execute. And it's going to do it. It's just going to repeat the same procedure, right? So this is very, very powerful. And I can just have, different, as you can see, I can have different tabs, and each tab can do like different things. So that you don't have to, like, every time you create a same plot, you don't have to do the same thing. You can just have a tab and say, execute this task. And even more helpful is that you can copy this into a Python script and run it, for example. It should be, you can record everything from when you like open the file, plot something, and then you can copy this into a Python script and paste it and then run that script. And then this is, again, precisely sort of the basis of the existing post-processing scripts. So hopefully you'll get a sense of what these scripts do and how you can do your own scripts. In fact, one of the exercises for this session will be just to create your own script to do something. All right. So we are going to leave it at that for now. And move on to go back to the presentation and do an in-class exercise. Okay, so let's try, this exercise. Let's give it like 10 minutes. So, go to visit, open the database that we've been using, remember, which is the alloy fluidification database, and then just follow these steps and just let me know what you see.
And feel free to ask questions, right?
Yeah,
if you're
yeah.
stuck somewhere.
Yes. Thank you, Vishwas. Yeah, you can ask by putting them in the chat, or also if you want, you can just unmute your microphone and feel free to just ask the question directly.
I have some difficulty with visit that the print or the font is much too large, so I can't see the whole window, and there's no scrolling on it. So how can it? Is there?
Oh, okay. Yeah, there may be some issue with the resolution of your screen. So in it may be like set to a very low resolution. In the installation guide for the virtual machine at the end,
I see.
I have a set of instructions to try to solve it. So maybe I'm trying to think how is the best way to do this. Maybe while people are, I can't unshare my screen, but If we go to a breakout room, I
Mhm.
can try to show you, if we go to the breakout room for a bit, I can show you how to
Okay.
how to do this. So if you can just join the questions room.
All right. Well, we don't have to do it now. I can do it later when,
Okay, that's fine.
you know,
Yeah.
everyone else is.
Okay. Okay. Basically, you can probably adjust the resolution in your virtual machine,
Okay.
and it should work.
I'm gonna, I remember now you have that on the email.
Yeah, I have it on the PDF instructions for installing the virtual machine.
Okay.
Yeah,
I'll have a look at that.
thank you. Mhm. Are you using Windows?
What?
Are you using Windows as your operating system?
Visit. I should have used my,
But do you have the virtual machine installed on Windows?
uh, yes, it's installed on Windows with.
Right, right. So that's one of the things that people were using in Windows were having issues with that. And you know, I think adjusting the resolution inside the virtual machine will solve the problem. Should solve the problem.
Oh, okay. It's a Linux, it's a Linux environment, but the virtual
Yeah.
machine.
Right, right, right. But
Uh-huh.
it happens for some reason. It happens on when the virtual machine is installed on Windows machines.
Okay.
So yeah, or in certain screens of I have used Mac and it worked. It happens under a certain if I use different screen, it has happened also that the resolution gets
Okay. I'm gonna
distorted.
I'm gonna have a look at that. But I've got, you know, well, I've got this. I've used it. I've used it, you know, to show those things on the visit. But I was able to go down clear to plot, but I wasn't able to go much below them.
Oh, right. Yeah, yeah.
So I was able to make those plots.
Right, right. Yeah, I'll be glad to help at the end of the session. If you can't figure it out still having issues. All right, how are people doing? Are you know, let's say who has finished the exercise? Who's gone all the way to step 10? Can you show of hands? Okay, so Buhari, you are. Yeah, or write a comment to say that you've successfully gone through each step until step 10. Okay.
Anyone who doesn't have any clue, you know, how to proceed.
Anyone who's stuck.
You can also send us a private chat. Are you facing issues with that, Buhari? Horizontal line that evolves? Or are you done with that?
No, I was just commenting what I'm seeing.
Oh, I see.
Yeah.
Okay.
Oh, okay. Cool.
Right, right. All right, I'm gonna give it one more minute. Two more. Yeah, as soon as you finish, just let you know, like maybe write in the comment chat, like I'm done. All right. Anyone else have any questions, or anyone else finish the exercise? All right, let's do it quickly. Let's do it quickly, and I'll show you what kind of there's kind of a point of this exercise. Oh, sorry, I was blocking the screen, I think. And the point of this exercise is actually to, all right, let me end the show for now. And then, so let's remove this plot, and then do what the exercise says, which is I'm going to add a concentration plot. I'm going to draw, go to the last frame, and I'm going to draw I'm going to draw a line out plot, which is this, at around 300, it said. Okay. And then this plot appears. But I'm going to set the limits of this. I'm going to go back to active window 2. And then I'm going to set the limits of this line out to be precisely 0, 300, and then 200, and then 300. You apply, dismiss. Let me do this thing where we see both of them. So as you can see, this is the line out. You can see it here, and the plot along the blue line is what you're seeing on the right hand side, right? So if you look at the evolution, you can see something interesting. You can see that, first you have, so we're only evolving the second plot. So you can see that, actually, let me go back to the first plot and then put it at the same time so that you can see what's going on, right? So as this peak gets here, now you start seeing a concentration value that is around, 1, a little bit less than 1, and then the concentration in the liquid jumps up to like almost 6 or 6.4 or something, and then it it decays from there until the bulk liquid. But one of the things to notice is that as this keeps growing, this is shifted to the right. But one interesting thing to notice is that the concentration in the solid, even though it's growing as the line is growing, it doesn't change the parts where it already solidify. So that tells us that there is a very low diffusion in the solid. So this is kind of one way that you can check that the solid, the diffusion in the solid is very small compared to the diffusion in the liquid, right? And this will be relevant for one exercise that I have for the end of the training session, or for if you want to take home. It's this behavior is kind of relevant to interpret the results. Okay, so I just wanted to show that. Let me close this plot. Let me close this second window, go back to the original configuration, and let me go back to the presentation. So the second example that I wanted to show you is that of nucleation and growth of precipitates in an alloy. So what we're simulating here is that is an alloying element that is originally in solid solution. So you have a matrix, it's all solid, and then you have a solute, but it's dissolved. Basically, it's in a region of the phase diagram where it's a single phase. And then what we do, what's called a quench into the coexistence region, where you have more than one phase that is stable. Now you have the matrix that's stable, but you also have a second phase, usually called beta phase, that is also stable. So a typical way in which this transformation happens is through nucleation, right? And so in this application is basically the results that I'm going to show you is from the an application that simulates nucleation of precipitates. And then after they nucleate, they will grow. And as they grow, they will deplete the solute that is around them. That's kind of that halo, that dark blue halo around the precipitate. So let's look at the database, and let's look at the plots, and I'm going to show you, I'm not going to do a lot of analysis on this. I just want to show you how the plot looks, because this is what we are going to analyze with the post-processing scripts. Okay, so let me maximize this. Ooh. No, let's not. Let's close this. Oh, first I have to delete all the plots. I'm going to delete, and then I'm going to close the database. All right. I still got a warning, but it was able to close it. I think I just closed it too fast. And then instead of this alloy solidification, I'm going to go to the folder called nucleation. And then I'm going to open the nucleation data. Again, it has a bunch of solution files that are grouped together. And then I'm going to just plot. I'm going to open, and I'm going to plot now. I'm going to do a plot of the order parameter. Okay. And draw it. Okay, so as you can see, basically it's just a homogeneous system. The order parameter is constant. It has a value of 0. And as time progresses, you're going to see how nuclei appear in the system. First one there, then one close to the edge, and then a couple more, and then a couple more. And then the ones that appear first start growing, right? And then, a lot more they just show up in random positions. But in general, this application is set so that the nucleation probability actually depends on the local concentration. So once all the solute in the matrix gets depleted or significantly depleted, the probability of nucleation will decrease, and we will stop seeing nucleation eventually. We're still far from that part, but it's going to happen if you just keep running the simulation. Now let's see a value of the concentration, right? And you see it's really the same structure, but by the way, here it looks like the matrix is changing color, but really the only thing that's going on is that the range of concentration is changing. So in order to solve this, we are going to just fix the value of the concentration. And actually, let's fix it from minimum 0, maximum 1. And let's just run this. And then here we'll see it's the same thing, but we're actually seeing how the concentration is a lot higher in the new phase, in the nuclei, and it's a lot smaller around the nuclei, right? Because all that solute had to come from somewhere, right? So in order to grow, they take up solute from the matrix. Okay, so this is just what I wanted to show you, and then I want to use this database to see an example of what the post-processing scripts do. So I'm going to go back to the presentation and talk a little bit about the post-processing scripts. So we have a suite of post-processing scripts in Python that calculate some useful properties of the system. And then these scripts use the visit CLI. You can look into this address to see where the post-processing scripts are located. And we have 4 post-processing scripts right now. One if you just want to plot and save all the images that you have, without having to even open visit, you can just run this using the visit CLI. Visit CLI is just something that you can enable in the terminal, and just by applying command lines, just by typing things in the command line, you can run them. I'll show you how to do that in the next slide. Then another one that calculates the interface area in 3 dimensions of or the length, the total length in 2 dimensions. There's one that calculates the phase fraction. So for instance, you want to calculate the volume fraction of solid, the volume fraction of liquid. You have to modify some of these scripts to get the area, the volume fraction of different phases, right? So you should be able to open these scripts, or at least look at them and identify the different the things that will go through one of these scripts, and then I'll show you what each line does. And then finally the last one that I want to show is like the domain statistics. So for example, in this nucleation example, we saw that we have several separate nuclei. So this application will count how many are there as a function of time, but it'll also obtain the average area or volume of these, and the standard deviation around the area. So some of these growth behavior or coarsening behavior are characterized by power laws. If I'm not mistaken, for example, growth is characterized by t to the minus 1/2, where like the average size is proportional to the power of time to the minus 1/2. So it's a very well-known power law behavior. And then in the coarsening regime, where like you stop nucleating, but these nuclei start growing, I think the growth rate is typically t to the power of minus one third. So having this counting and also obtaining average area or volume of each domain helps us, look into whether these to identify these regimes. All right, let's go back and go to the machine, the virtual machine. So I'm going to close visit now. Okay. And one of the things that I actually need to do right now is and I want you to also do that before we do the before we apply the post-processing scripts, is to update the GitHub repository, because today I fixed a small typo in one of these scripts that makes it get stuck. So let's go to tools. Well, let's go to the home directory, then tools, and then phase field. Okay. And then once I'm in that directory, I am going to do a git pull, which will just update the repository. All right. And it'll update one of the post-processing scripts. Okay. Which is this one, interface area. All right. Now that's all I wanted to do. And now let's go back to our training data. I think it was called, the directory was called PRISMS-PF training materials, and then nucleation. I think it's called training data, and then nucleation. Okay. And now that I'm here, I have all these images that we already opened with visit. And let's actually copy all the scripts that we have in the post-processing directory. Let's copy them here. So I'm going to go and copy everything that is on tools, phase field, and post-processing. All the Python files, I'm going to copy them here. Okay. And now if I do an ls, you'll see these new files here, which are the post-processing scripts that I was talking about. Okay, so in order to run them, I also have this on a slide that I didn't show, but all you have to do is type visit. Let's do the one that plot and save. So you just do visit and then dash CLI, which is the keyword for command line interface. And then let's do S, which is dash S, which means that it's going to load a script. And then let's just do plot and save. I hope that this works. And this is just going to open visit, plot all the times, right? And just save all of these in images. Okay. So if you can see, there are new files. There should be new files in this directory, and these new files will be the files for each of the frames that corresponds to each of the solution files. So we can actually see what these frames look like. Let's go here, training materials. Open this, training data, and nucleation. And you can just open either of them. And there it is. You can also later create a movie. If you have a movie maker, you can create a movie of these files, or you can actually create a movie on visit as well. But you have to look into that, or if anybody wants some help with that, I will be glad to help. There's a movie that I already created, by the way, for the concentration. You can see here. Okay. Let's just go back. I also have another option. Let me actually just remove this. Remove these new files. And there is another option to run the scripts, but suppose you don't even want to see the visit window. I can have the option -no win, and then it'll just do this all in the background, and you don't even, it doesn't even have to open visit, and it can usually be faster. Okay. And as you can see, there will be new files as well. Same files, exact same files that you can see here. Okay. All right, let's try other scripts. So let's try visit CLI. I'm not going to use this no window option because I want you to see what's happening. But let's look at interfacial area. Okay. So as you can see, it's doing a contour plot, and then it's actually summing up the length of these domains, which are basically the length of the interface. And as it's expected, so here it's plotting the frame number, the time corresponding to the frame number, and then the amount of area. Since we don't have any nuclei at the beginning, it starts with 0, and then it starts increasing and increasing as the nuclei start getting bigger, right? Which is what's expected. Let's do the phase fraction, which is going to calculate the fraction of basically the total area of the nuclei divided by the area of the total area of the system. Again, if we had 3D data, it'll just do exactly the same. You don't even have to change anything. So there it is. So again, it's very small because the nuclei occupy only a very, very small fraction of the system. But as you can see, these numbers keep increasing. Okay. And then finally, let's plot the domain statistics one. And this will just count the number of nuclei and calculate the average size and standard deviation with respect to the size. So again, the first number here is the frame, the time. This is the number of nuclei. You have 1, right? The amount of the size of the nuclei. Since we only have 1 nuclei, obviously the average is the only sample that we have is the average, and then for the standard deviation will be 0. Once we have 2 nuclei, we can calculate a standard deviation of that size, around that size, right? And then obviously the average size is also something that should be monotonically increasing for it to make sense, right? Okay. Actually, no, that I am actually wrong about that. For example, if you can see in this case, we have an average size of 134. And then next time I have 131. So can somebody explain why the average size decreased? Anyone? Well, I can tell you, if there's no volunteers, I can just tell you that the reason it decreased is because there were new nuclei that appeared, right? So those new nuclei are small relative to the nuclei that have nuclei that have already grown, and therefore they bring the average down, the average size down, right? And that's the reason this decreased. In this interval, only 1 nuclei from, from the last 2 lines, you only have one nuclei that appeared. So, and then all the other ones grew. So that's why the average size grew in this case. So these are all the post-processing scripts. Let me actually just show you how they look like. I mean, you can just point at one that's kind of simple. Let's just pick the phase fraction, just to see, so that you're able to, the idea of the scripts really is not to just use the ones that we have, but to sort of, you take them as, it's kind of like applications. You can take them as templates to do whatever you want, right? So you can make, sophisticate the scripts that are sophisticated for the application that you want to do. So let's go to training data here. And I want to show you some of the scripts that we have. I just want to show you, for example, the one that's called interface phase fraction is a good one. Let's see this one. And what is it doing, right? So apologies for the fonts, kind of annoying. But yeah, basically what we're doing is everything we're doing is just visit commands that we can load using that commons window. And then, so we're opening the database, right? We have to be in the directory. Then we're going to plot, we add a pseudocolor plot of n, which is the order parameter in this case. So you have to be careful, because if you have a simulation where you have a different order parameter name, you have to change this. You have to go in and change the order parameter name for this. Then it asks for the grid information. And then this will actually extract the number of grid points in each direction, right? And then that will tell us if this is a 2-dimensional system or a 3-dimensional system. And then if it's a 2-dimensional system, we want to first calculate if it's a 2-dimensional system, we want to calculate the volume of the system. But if it's a 2-dimensional system, we want to calculate the area, again, using that query. Remember, we did that. Then we're going to initialize this vector, the phase fraction vector. And this tells us the number of frames that we have that we read, right? So the number of output files that we read. Then we're going to open a file for writing the results. And then we're just going to say we're going to open that file to read. And then the file is going to be phi. Usually phase fraction is denoted by the Greek letter phi. So let's just use that one. Versus time. Again, you can change anything you want in here. And then here's a loop that is going to go through every state in this time slider range. And then set the time slider to the corresponding state, and then tell me what the time is for that state, right? And then the time will be that result. Then tell me what the weighted variable sum, which, if you remember, this is the total integral, right, of n. But is this going to give me the area or volume of the region where n equals 1, right? And then save that result. And then it's going to calculate the phase fraction as the value of the total fraction, the total volume of that region divided by the total volume of the system. And then just, outputs, closes, deletes the plots, and gets out. Yeah, and that's it. You can look into, I encourage you to look at other ones on your own. and see what they're doing. I try to, you know, put a lot of comments in them, but if there's parts that you don't understand, I'll be glad to go over them with you. All right, so that's the post-processing scripts. Yeah, so this is the slide that I didn't mention, but I already explained it. So, but it's here for you to, when you get the slides, if you want to just look at the slides, if you don't remember what we wrote, all you have to do is copy all the scripts that you have, or you can just copy one of the scripts, the one you care about, where your files are located, and then just run them using this. So this is going to be just our last exercise, and then I think we can just leave it here, and this is a more challenging exercise where you are going to compare, the curve of solid concentration for the simulation data that we have against the Scheil curve, and plot the results. Save the results and make a plot of the results. You can plot these results in Python or any other MATLAB or whatever you want. If you want to plot them, actually, let me just take a quick break. If you want to get things outside of the VM, my recommendation is you should have drag and drop enable. So let me show you how this is done. So what I do usually is I just put it on the desktop. I put a file on the desktop. So let's see. So I have a movie, right? So let me just move a frame. So I'm going to move. I'm going to move or copy this frame 10, to the desktop area. Okay, and as you can see, it appeared here. And then I can just drag this frame outside to your own desktop. And then you can, that's what I'm saying, when you get your results, you can just drag them out. I think this didn't work right now for some reason. Oops, I think I know what the problem is. I think this only works if you drag it to the sides, not the bottom, for some reason. So yeah, just remember not to do that, not to drag it to the bottom. But anyway, that's one way to transfer the data. Of course, you can just email it to yourself if you want, or some other way. But drag and drop seems to be the simplest way. So I'm actually kind of stuck, I think, in the VM for trying to do that through the bottom edge. So I'm gonna just shut it down and reopen it. But in the meantime, I'll just show you the exercise that we have on PowerPoint.
And then I would encourage you to install it locally, Prisms on your computer.
Oh, right. Yes,
Yeah.
of course. Mm-hmm.
Right. I mean, that'll give you much more freedom than
Mm-hmm.
just using a VM. VM is good for running some basic stuff if you want to
Yep.
get familiarity and if you just have very few small problems to deal with. But
Mm-hmm.
then installing it on your own machine would give you a lot of more freedom to build new applications, play with this wizard thing, and then you can automate the entire thing right from beginning, like changing the parameter file to running the simulation, and then in the end to analyze and visualize it. You can do all of that in just one bash script.
Mm-hmm. Yeah, thank you for that, Vishwas. Yeah, so any questions so far? So I'm gonna just we're gonna just use the rest of the session for you to try this problem, or if you were behind the other problem as well, you can just try it, and actually let me exit this so that I can have space to maneuver. So yeah, just try this problem. If you have questions about the problem, you can ask me, or you can just, if you want to, just leave now and try it at home. Well, you probably are at home, but if you want to try it on your own, you are welcome to, and then you can just ask us questions about it. One of the things that I wanted to point out, and it doesn't seem like there's a slide here for that, but is that there is an interactive, oh, yeah, this one. So there will be a Q&A session for all the PRISMS tools, and that obviously includes PRISMS-PF on Friday. If you have any remaining questions, you can ask us there. But of course, if you want to, you can always email me directly. I'm gonna just put in my email here. Or you can just email the PRISMS-PF mailing list. And we will be glad to help you out. Okay, and that is, I think we're just going to leave it at that. Thank you everyone for showing up, and hopefully it was helpful to give you an idea. Also encourage you, of course, to watch the videos in the YouTube tutorial and to read the PRISMS-PF manual, where you can learn a lot more about the functionalities in detail. So at any point, if you have any questions, just send us your questions through the chat, and we'll stay here until 5, and then we can just answer them here. Yes, we will be getting the recording too. I will share the recording as soon as it's ready. Actually, let me stop the recording now. I think we can stop it.